Okay, folks, welcome back. And in the past video, we talked about this whole concept of what happens when a molecule first enters into the mass spectrometer. So we said that the molecule goes into this entry chamber and it gets slammed with an electron beam at 70 electron volts, and a tooth gets knocked out. And that tooth is an electron that will end up getting removed, and we have this positively charged compound that's still present. And we call this a radical cation, or really a molecular ion, is what most people refer to it as. And we said that the positive charge has to be on here in order for the molecule to do what it needs to do. All right, well, that's only one option. That's where things get a little complicated here. So option number one, the sample goes in, the sample becomes a cation, and then the cation gets detected eventually. There's a second option, though. We could have a molecule. That molecule could come into the chamber of the MS. The electron beam could slam that molecule. And instead of knocking out a tooth, it could just really bust its face up into pieces. That's a little more violent. But sometimes this is what happens in a fight. Sometimes you escape with very minimal bruises. Other times you'll leave and you'll need to go to the hospital for facial reconstructive surgery. Don't ask me how I know that. So this molecule could not just lose an electron, but it could actually fragment, break up in pieces. But you know, the still same thing kind of exists here. One of these pieces will be negative. One of these pieces will still end up being positive. And then away that positive goes. It acts just like the molecular ion that we talked about before. It goes down to the detector sees it, and it measures it. But here we're losing a part of the molecule. It's not just a simple electron that's getting lost. It's actually part of the molecule that has been broken off, that carries a negative charge, and that will never be seen by the detector. This is what we would call a fragment or a fragment. And there's some molecules that will only fragment in one or two ways, and there's other molecules that will fragment in probably 20 or 30 different ways. And what we typically look for is something called a fragmentation pattern. They all will break up a very specific way. They will give me different signals when it reaches the detector, and the detector looks at that fragmentation pattern and it matches it to what it knows in its database. There's things that we can take away from the fragmentation pattern, and we'll begin to look at those. But this is why we're going to see more than one signal on the readout. So I'm going to fast forward just a little bit here on you. And what the signals will look like, molecular weight will be down here at the very bottom. And let's say the molecular weight of this compound is 79. We'll keep it easy. Well, if I only go by option number one, the sample goes in, creates a cation, it just loses an electron and that's it, then the detector is going to see it. The only signal that I would see would be at 79. But that is not what happens. In a simple world, it will be. But you know, here's the thing. I'm glad it doesn't do that. And the reason is because there's so many different things that maybe could weigh 79. So how would it be able to determine what that specific compound is? It cannot do that by just the molecular weight alone. It has to look at fragmentation patterns. So now what will happen is that sometimes this molecule will enter in, it will lose a tooth, we'll get a positive read at 79. But sometimes this molecule comes in, it will get into a fight, it wasn't ready for it, and it loses more than just an electron. It actually loses a piece of the molecule. So yeah, some do come through, and we do see a signal here at 79. But we could start seeing lines and signals to show up at other places as well. And all of these would be different numbers, every single one of them. And each one of these signals will be contributed to the fragment that's getting created when the molecule goes across that electron beam. That is where all these lines are coming from. If we just relied on molecular weight only, we could limit our choices, but we could not completely identify the molecule. But molecules fragment a different way, all of them, even the ones that always 79. If it's a different molecule, it will fragment differently. And that fragmentation pattern is really what we're looking at to cross-reference in our database to determine the identity of the compound that has been entered into the mass spectrometer system. So that fragmentation pattern is pretty important. A lot of people hate it. A lot of people do not like the idea of seeing multiple lines down here. But if it wasn't for these multiple lines, the mass spectrometer would not have the power that it does today. That is a very important aspect to the mass spectroscopy system. Okay, now with that said, let's talk about the remnants. So in the first encounter, we said that we lose an electron. In the second encounter, we say that we get fragments that carry a negative charge. There's also a chance that we will get a molecule that goes into the system. It gets hit with an electron beam, but nothing happens to it. Statistics tell me that can happen. No teeth get knocked out. No fragments get shot off. The way it entered is the way it leaves. It does not carry a positive charge. We got to get rid of those. The only way that this mass spectrometer works is by looking at the positively charged species. If it's not positively charged, too bad. It's never going to see the daylight of the tunnel at the end. So all three of these cases have to be sucked out of the instrument. And that is done by vacuum. So we have to have a vacuum hooked up to the system. We have to make sure that it is capable of sucking out all of the trash that will go into the mass spectrometer system. And the only thing that we want are the positive charges to reach the very end. Now, the vacuum's not the only thing that's going to do it. The vacuum's going to help pull it out. But there's going to be another piece in there that's going to help us with this kind of cleanup process before it reaches the detector unit. So we need to talk about that piece. But this is one of the reasons that a vacuum is going to be present. So, before we get to that part, now that we understand this fragmentation pattern, the question that many people have is that, can I predict it? Or do I have to rely on the instrument to do it for me? And the answer is no, you can predict it. You can take a look at some molecules. You can kind of determine where they would cleave if they're going to break apart. And you can kind of visualize and maybe reason out some of the numbers and some of the signals, some of the signals that you'll see here. No big deal, right? And eventually we'll get to that point. But I want you to understand that, yes, you can predict some of these fragments. Yes, you can kind of already understand what numbers will show up on the spectrum before you even inject the sample into it. And we're going to have to learn how to go through some of those processes. Not only that, but with these fragmentation patterns, keep in mind we keep talking about isotopes, right? And isotopes way different. And you're probably wondering, well, why did I even go into this discussion? Well, I told you there was a carbon-12 and there was a carbon-13, right? So let's say that we've got a methyl group, a CH4 group that we have inserted into the MS. Well, if I told you to do the formula weight for this, you would go, well, that's pretty easy. I've got one carbon, it weighs 12.01 times 1, so we'll just round it off to 12. And then the hydrogens weigh 1, and there's 4 of those. So 4 and 12 is going to be a total of 16. So on the mass spectra at spot number 16, I would probably see a positive signal to show up. That's the formula weight for the methyl group, right? The problem, though, is that it's not as simple as that. And that's because of the isotopes. Yeah, carbon weighs 12 most of the time, but you know what? Carbon also has a 13 that comes along 1% of the time, as we learned in a previous video or two. So because of that, there could be a small little tick mark right beside of that big major line. And that's going to kind of dirty up our spectra a little bit. But that tick mark is present because that is representative of isotopes that are present in these molecules. So for instance, at 79, I just wouldn't see a 79. I would probably at least see another little spike to the side of it, one more, greater, maybe at 80. I could maybe see some at 82. I could see some a little bit down here below or a little bit below that. But I'm going to see these very minor lines to show up on either side, and that is why they are present. It's all due to the isotopes that are naturally found in these molecules. Every now and then, a methane group is going to have a fat carbon with it and not the normal skinny carbon that we always typically see. That also happens at every single fragment. So I would see small lines and tick marks to each side down here, but I would also see the same tick marks and lines on each side of those major lines. And this is going to complicate matters up just a little bit. Nothing major, but that is why they're going to be present. So when we eventually get to the point where we're analyzing mass spectra and figuring out what fragments are leading to what peaks and positive signals, then we will have a clear understanding of what we're looking at. All right? So that's the concept of fragmentation. We are going to see major peaks, not just one, but multiple ones, show up on the spectrum. And then beside of those major ones, we're going to see tiny little bitty ones. And those tiny little bitty ones are coming from the isotopes that could be present in that compound. They're naturally there. We cannot get rid of them. They're going to show up on the MS because its job is to determine the difference in the masses. And it knows the difference between a formula weight of a 79 and the formula weight of an 80 and the formula weight of a 78. And it's going to show it every time that it happens. All right? Okay, so with that said, we're going to stop here. You've got maybe a better understanding of what's getting ready to happen. And before we go on and talk about the next piece of sucking these things out and what's doing it, now that we've talked about the concept of fragmentation, we need to kind of talk about how to make sure the machine's going to do its job the proper way before we go even further. So in the next video, we'll talk about something called a tune.